What is the electron configuration for sulfur with 16 protons and symbol S? The way we're taught in the textbooks for the last century has been something called strict aufbau. Now, aufbau is the German word for filling or ordering, okay? And in part, basically, it becomes this abstract system of numbers with 2, 6, 10, 14, and such, but building up in sort of a straight then diagonal process. So subshell S has 2, subshell P has 6, subshell D has 10, and subshell F has 14. And those you fill 2, and then it's full. Then you fill 2, then 6, 2, then 6. And strangely enough, you do 2, then 10, then 6, then 2, then 10, then 6, and so on, 2, then 14. And this is the strict aufbau method. Now, these strict aufbau rules are very abstract. You're working only with numbers. And the first and important rule is that partial subshell filling is allowed. You see, you go through this 1, 2, 1, 2, and then you could just go 1, 2, 3, 4, 5, 6, then that one's full, you move on to the next. Okay, and this is the method of the strict aufbau method and that system. And then, as I said, the fill order is S, then F, then D, then P, with that D filling with N, but having energy of N minus 1, and F, N, and energy of N minus 2, which is partially why I have these tails sort of going up, so that the energy here is 2 above the energy here. So shell 6's 14 has the energy like shell 4's 6. Now, instead, I take subshells as a 3D engineering project. I want to give you something more than the abstract that you can understand. Okay, it's very similar, but it adds a 3D model. Specifically, that subshells are longitudinal rings of electrons. Okay, that if you have electrons and they're sitting at the same inclination or longitude angle, remember, inclination is the angle from the pole, and longitude is the angle from the equator, which effectively are just complementary, and also the same distance, they will all have the same energy. So that means all these electrons have the same energy towards the nucleus, and thereby the same energy to release to infinity. And so thereby we group them into sets that we call electron subshells. Now, I go a step further, and I say that this set is my interpretation of the Nobel Prize winner Bose's 1924 paper that was a proof of statistical methods. And in that paper, he used 2 words that caught my eye. One is a cylinder surface. Well, a cylinder surface looks like a longitudinal ring. It stays a certain distance axial away from this nucleostatic axis of the nucleus. And then he said, oh, well, I have to multiply my results by 2x for something that seems like polarity. Well, that's 2 hemispheres, this balancing. And this balancing is very special because it offsets by 1/2 phase. You see, this one is front and that one is back, so that they line up so that with the nucleus, they're exactly there. So you have electrostatic balance, plus here, minus here, and the 2 pluses here in the middle. So there's no global field. It's an electrically balanced system, only localized events, which are these rings. Now, this idea that you have multiple rings that all want to be pulled into this axis, but guess what? They bump off of each other in units of electrons, quantization. So the quantization and the methods of quantum mechanics is just that. In fact, that equation is really the logic from Euler that if you have a particle and there's some axis that it seems to always be going towards, you use the equation with e to the ix, and I being this invisible number. I hate the imaginary number word. That invisible number is because you don't know what that is. Now, in my work for advanced students, you can see that that particle 2 is the nucleus, and thereby I can replace the Schrodinger equation with a deterministic result, but that's for later. So this becomes a 3D system that's similar to this. It still has those growing shells, but it's no longer an abstract system. It really is 3D. Now this is one hemisphere. There is another hemisphere here off of the paper to the top, okay? And now, instead of going 2, 6, 10, 14, this hemisphere goes 1, 3, 5, and 7. Now, those numbers work because 1 is 1 squared. 1 plus 3 is 4, which is 2 squared. This is fun math. 1 plus 3 plus 5 is 9, which is 3 squared. 1 plus 3 plus 5 plus 7 is 16, which is 4 squared. And that comes because this is a bubble, a circle. And you're growing in 2 dimensions. The tightest configuration in 2 dimensions is pi times radius squared. And in the 3rd dimension, you have 2 hemispheres, here and here. And so thereby, when you look at a periodic table, it's built 2 times squares for full shells. Now that's a little incomplete because I told you about this offset by half phase here. That means that you sort of get a path 1, 3, 3 because those half phases, if they were like this, but when you do it like this, they can fit in between each other. So the path on the axis, on the nucleostatic axis, goes 1, 1, 1, 1, 1, 1, and they're very much aligned. However, going here, you go 3, 5, 3, 5, 5, 7, 7. So as a result, the distance off axis for these is slightly less. So it's not really hemispherical, but I just don't like the word hemi-oblongal. Anyway, it's strange. And that leads you to the last rule from Aufbau that this model provides, and that is these shells are like n minus 2. And here, wow, is just like n minus 1. So we still meet all the rules that were discovered, okay? We don't break anything. We don't break statistical mechanics. We don't break Aufbau. But we now have a 3D model that allows me to engineer these calculations exactly. So specifically, I've gone and created the Arno-Dot-Diagram. And that's a way for us to build these in a little flat, but you get an idea of these. This is different than the Lewis diagram, which is 2, 2, 2, 2, trying to do octets all the time. Subshells don't build in there. And it confuses students because it has 2 electrons on one side. But that second electron is all the way over on the far side. And so through the nucleus at the opposite hemisphere at the 180 degree. You can see this here in that this one is down and that one is up, okay? And these are matched sets so that there is always linear balance or radial balance for electrostatic, other than the localized if you're like really close to this one, okay? So now, so each of these is one of those rings. However, there's one extra thing, and that is a transitional equatorial subshell of 3 here. Now, normally you have 2 hemispheres. So that means you get counts that are always 2 times, okay? Which is fine, you can figure everything out, but there are odd count elements. And so partial subshells have, if there's a distance of 0, you don't get the pair. So there can be a 3, and that's how you get the odd count Electron subshell exceptions to the strict aufbau. But I have a 3D model that explains it, and that's what we're trying to help do. So basically what happens is you count up those different things. Again, only full subshells. The preference is the tightest fits, and that is going from the pole towards the equator as the general preference, but knowing that you can only have fulls, okay? Which is a little strange because, for example, if you have a 10, well, those, you can't do 1 plus 3, 1 plus 3, but you can do 2 times 5. And so the rule of full subshells overrides the tightest fit. So specifically today, I wanted to talk about sulfur. And you have now the background to understand what I'm going to talk about. All right. So sulfur in a contributing, for example, a sulfur fluoride with 6 is plus 6. So that outer ring is contributing versus receiving. And I show that as the faces of a cube. Now remember, I have different layers. The first layer 2 becomes a cube, and that octet you've heard about. But what happens with 6 is that there's a position on the face of each cube, which can have 1, 2, 3, and in the back, 1, 2, 3 positions. So for sulfur, it works out better for it to be a little pyramid. So you have the 4 corners, that's in the back, as the base, and 1 electron sits at the top of that pyramid. And so I call this the faces of the cube positions. Again, the rules apply. You also potentially, in shell 3, have this equatorial, but it's really an either or. You can't get the faces and the equatorial because those counts, that would be a 6 plus 3, which is 9, and we only can get 8 in that shell, okay? But basically, with those, you can get all the counts of the different ones. In this case, you don't get the 2 at the poles, you get 6 at the faces, 3 plus 3, and you don't get the equatorial. So 0 plus 3 plus 3 plus 0 equals 6 outer ring shells by the shell 3 template, okay? Now, that is rare because it really has to be through something that is pulling 6 electrons into their positions. What happens the other way? Because sulfur usually you would think of as a -2 because it only takes 2 for itself to be full. So what happens with that? So this is the electron configuration using the same Arno-Dot-Diagram, shell 3 as receiving. So this is, in this case, the pyramids are full, but I still have 2 positions. So what's left open is those 2 at the poles. So these are full, and that's your receiving blue positions. So it becomes a polar bond. Now the thing is, again, the strict aufbau says that it's 2s2, 2p, 4 of 6. Okay, Wikipedia supports that as the current, there's no exceptions known. However, as you can see, I show the 2 as an S0 and the 2F for faces 6, and again, always full or always empty, no partials. Thank you.